We're going to start our AP review by looking at the 2001 free response, problem number 1. Now I'm going to try to select a smattering of problems that run the range of free response problems. Sometimes they're going to have you looking at a graph, sometimes you're going to be dealing in numbers, sometimes you're going to be dealing in just variables. So as we begin the AP review, I'm going to try to pick on every single type of problem. This first problem is all about reading graphs. We don't really spend a whole lot of time doing it in class because we rely on the calculus, but this is a good refresher for how to read a graph, how to use the information inside of the problem. Okay, so for this one, we've got a motion sensor, we have a cart moving forward, it's going to crash into a force sensor, and it's going to be repelled backwards. We have two graphs here. We have a velocity versus time graph, and we have a force versus time graph. Right away, when I see velocity versus time graph, I think about the slope being the acceleration, the area under the curve being the displacement. So that's what my brain is already focused on. For the force versus time graph, I immediately think about change in momentum. Force versus time graph is change in momentum. So that's where my headspace is right now. The best thing you can do on these free response problems, read them first, take a deep breath, think about them, and then come back to them. You have 3 free response problems to attack in 45 minutes. That means each one should take about 15 minutes. And just because you can't get part A doesn't mean you can't get part B. So you want to take what I call a shotgun blast approach to these problems. Try to do as much of them as you can. Don't leave anything blank. It's very similar to my tests. I've been preparing you for this all year. Okay, first thing, determine the cart's acceleration between 0.33 seconds and 0.37 seconds. Okay, so when it comes time to figure out acceleration, I know that acceleration is equal to delta V over delta T. So if I figure out the change in velocity and the change in time, I should be able to figure this out. We're going to estimate because we don't have exact numbers in the graph. That's all they're looking for is an estimation, okay? At 0.33 seconds, it looks like the velocity is about 2.2 meters per second because we're just a little bit above the 2 line we're estimating here. And then the velocity at about 0.37 seconds is a little bit around negative 0.18 meters per second. So the change in velocity, V final minus V initial, is negative 1.8, that's the final velocity. We subtract the initial velocity, about 2.2 meters per second. The time interval, the time interval from 0.33 to 0.37 is 0.04. So we got something that looks like that, okay? So just checking my work here, want to make sure I'm doing this right. I don't have a calculator in front of me. That should be about negative 0.4. Negative 0.4 divided by 0.04, which is going to be about negative 10 meters per second squared, okay? So they made the numbers really nice here. They're not expecting you to use a calculator for much of this. What I did here was I figured out the change in velocity, the change in time from the graph, okay? Determine the magnitude of the change in the cart's momentum during the collision. Okay, for momentum, I'm either going to use mass times velocity. I don't have the mass of the cart here, so I can't do that. Or I remember that a force versus time graph is going to give me, the area under the curve, is going to give me the momentum change, okay? So let's take a look at the solution here. How did they do it? For some method, average force. For the okay, so they did an average force inside here, which is totally fine. I think that that's a fair method for doing it. Just want to make sure here. Do I agree with doing it that way? I would do the area under the curve in order to figure this out. So if I do the area under the curve here, I have kind of a triangle sort of shape. So I would maybe just estimate it as 1/2 base times height. Or if you really wanted to get as close as humanly possible, you'd figure out the 2 triangles on the sides of the force versus time graph, the rectangle in between, and then the huge triangle. Let's try to see what they did here. Looks like they just did the integral for any indication of the concept, okay, for a correct numerical value of 0.6. Okay, that seems roughly about right. Just finding the area under the curve. Yep, I agree with that. You just find the area under the curve. I would just do it as a triangle, go from there, estimate it as best you can, okay? Now, for figuring out the mass of the cart, that answer, by the way, the change in momentum for the area under the curve. They're looking for an answer of about 0.6 Newton seconds or kilogram meter per second. Something along those lines. Now, determine the mass of the cart. What they're doing here is they're combining the two things that you've already done, part A and part B, to try to figure out part C. Now, if you panic, if you didn't get part A or you didn't get part B, you can still set up part C in order to get some points. So just because you can't find an answer right now doesn't mean you should stop. You should still put down your work, correctly label it. Okay, for determining the mass of the cart, we can do it a couple of different ways. The way I would do it is we know that the change in momentum would be equal to the mass times the change in velocity. We know the change in velocity, we did that up here. We don't know the mass, that's what we're trying to find. And we just found the change in momentum in part B. So now I have 0.6 is equal to the mass multiplied by the change in velocity that we found up here, which would be 0.4. I'm not worried about the minus sign right now. But 0.6 is what we found in here, the area under the curve for the force versus time graph, and 0.4 up here for the change in velocity. That's going to give us a mass of about 1.5 kilograms. Okay? So I'm combining part A and part B in order to figure out part C. Are there other ways of doing this? Yes, but I think this is the easiest. Determine the energy lost in the collision between the force sensor. Okay, they've been talking about momentum for a long time. Now they're going to switch it around and they're going to talk about energy loss. There is only kinetic energy in this problem. There's the kinetic energy initial, the kinetic energy final. They're not equal to each other right now, and you can tell because the velocities have changed. So if you find the kinetic energy initial and subtract the kinetic energy final, you get the change in energy. So the energy lost is going to be equal to the kinetic energy initial minus the kinetic energy final. The kinetic energy initial is 1/2 the 1.5 multiplied by the velocity squared at the start, which was the 2.2 squared. Now we're going to subtract the mass, 1.5, multiplied by the final velocity. It is negative, but since we're squaring it, it doesn't matter. 1.8 the quantity squared. And we crunch these numbers. Again, I don't have a calculator up here. I don't really care. And we get an answer of about 0.012 joules. 0.012 joules. Okay? So part A, using the graph to figure out the change in acceleration, initial velocity, final velocity, time interval. Part B, area under the curve to figure out the change in momentum. It's a little complicated, so I would probably just estimate it instead of figuring out all those shapes. Part C, figuring out the mass based on change in momentum would be equal to mass times change in velocity. The mass is not changing, but the velocity is changing. And down here, the energy lost, we just find the change in the kinetic energy and the final kinetic energy. Okay? Very straightforward problem, but a lot of graph reading here.